Hi, my name is Yiheng, a first-year PhD student in the Mechanical and Aerospace Engineering Department at University of California, Irvine. I'm so glad to represent my work on the second international conference on energy and AI. So the topic I'm gonna cover today is probing the liquid water quantification in polymer electrolyte memory fuel cells using the convolutional neural network, which is CNN. And Professor Wang is my supervisor. So first, let me start with the motivation. So the polymer electrolyte memory fuel cells, which is the PEM fuel cells, are electrochemical devices that convert the chemical energy stored in a fuel directly and efficiently to electrical energy with water as the only byproduct. And figure on the left-hand side shows some applications of the PEM fuel cells, including the transport power, the portable power, and the backup power, like the fuel cell vehicles or even the fuel cell military equipment. And there is a typical PEM fuel cell shows on the right-hand side, compressed bipolar plates, gas diffusion layers, which is GDL, with macroporous layers, which is MPL, and a polymer electrolyte memory coated with the catalyst layer. And hydrogen fuel is injected into the anode gas flow channel, which is GFC, and diffuses across the GDL and MPL for the hydrogen oxidation reaction in the anode catalyst layer. Well, the ambient oxygen is fed on the other side of the cell for the oxygen reduction reaction in the cathode side catalyst layer. And all papers that have ever worked on the two-phase flow for the PEM fuel cells, they gather information from the image processing methods, which has some disadvantages, like they need to change filters in each test with a high computational cost and a low accuracy. So in this paper, we train a CNN model to predict the water content in the PEM fuel cells. And here are some introductions about the two-phase flow in the PEM fuel cell. And the figure here shows the two-phase flow in the PEM fuel cell. The produced water is transported across the GDL, the gas diffusion layer, to the GFC, which is the gas flow channels. I'm sorry. Yes. So the produced water is transported across the MPL and the GDL to the gas flow channels, in which it is removed out of the cell. And the water content directly affects the protonic conductivity, but excess water will lead to flooding of the electrode and blockage of the gas flow channels, happening the reactant gas transport and supply. So probing the water content in an operating fuel cell is important. And there are some methods have been proposed to detect the water content in the operating PEM fuel cells, including the optical methods, the neutron radiography imaging methods, and the X-ray radiography methods. So in this paper, we trained the CNN model to learn the neutron radiography images to get the water content in the PEM fuel cell. And in this page, it shows how we use the neutron images to train the CNN model. Like first, we need to get the input layer, which is the neutron images. And after we got lots of the images, we put the images into the convolutional neural network. After several layers, we can get the water areal mass density. And also the softmax activation function has been used for the CNN model. The function shows here, and which is the last layer of the CNN model. And also the loss function shows here also has been applied to predict the CNN model accuracy. So before we train the model, we need to pre-processing the data set, the images to form a data set. So figure A shows the neutron images from the Mishler, and we use lots of this kind of images to train our CNN model. So the neutron radiography images are divided into are divided into 10 classes. So in each class, there are about 100 images. And so the total is about 1,000 images to train the model. And 70% of the data set is used for training, and 30% of data set is used for testing. And after the model is trained, we will input a raw image to be analyzed to get the water aerial mass density. And before that, we need to divide the raw image into 36 small parts in order to increase the accuracy. And here's the whole training process of the CNN model. So first, like I said, we got lots of neutron images and divided into 1,000 parts. And then we can get the data set. So 70% of the data set is used for training, and 30% is used for testing. And then we can train the CNN model. And after the model is trained, we need to input the raw image, which will be divided into 36 parts into the CNN model. And then we can get the average water aerial mass density of the raw image. So here are the results of the CNN model. On the left-hand side is the confusion matrix generated by the test data. So in the confusion matrix, we can clearly show that most of data is more than 93%. And after calculation, the prediction with accuracy of 95% of each class by a loss function is for the CNN model. And we also compare another image processing method, which is called pixelation method. And figure on the right-hand side shows the water aerial mass density of RH 50% and 100% using CNN and pixelation method. So we can say it shows a similar result. And the CNN model showed an agreement with 91%, which means the CNN model is acceptable to predict the water distribution in the PEM fuel cell. So in the future, we're gonna train another model with boundary deletion, which will increase the accuracy and the stability of the model. Because some images in the data sites which near the boundary will cause the misunderstanding for the model. So we're gonna train another model with boundary deletions to compare with the accuracy between two models. And we want also improve the accuracy of classification of images from 10 classes to more classes to see how it works. And also testing the PEM fuel cells with X-ray radiography and optical sensors are considered as the future work. So here are the references I used for this paper. Thank you. Thank you for listening.